Welcome to Space to Ground. I'm Ana Cristina Olvera, coming to you today from the Mission Control Center at NASA's Johnson Space Center in Houston, Texas. It's from this very building that flight controllers oversee the status of the International Space Station and its systems, including monitoring the health and safety of the astronauts on board. In fact, the health and safety of crew members is one of the primary areas of research aboard the space station. Every aspect of how our body reacts to microgravity is studied, but arguably none more so than the heart.
All right, lift off and the clock is started.
From the early days of human spaceflight, researchers studied how the heart reacted to microgravity. They monitored heart rate and blood pressure changes before, during, and after spaceflight in order to see if the human body could survive living in space and the extreme G-forces during launch and landing. So we happen to be here on Valentine's Day. So what better time to talk to you about affairs of the heart? But instead of chocolate and flowers, we will take a look at heart health and the research taking place aboard the International Space Station.
First of all, think about fluid shifts. We go from Earth's gravity to no gravity, and what does all that do to the fluid in our body? We think about changes in our vision. We think about muscle atrophy or bone atrophy. And so we have to think about all of the ways that we counter that. But maybe for Valentine's Day, we could just talk about the cardiovascular system. So we know a lot about those changes in the microgravity, those fluid shifts. We have to think about some of these risks that are associated with that. So for example, there could be a chance of vein clots or blood clots, and how we monitor that is through ultrasound. Another example is that when we land, there are that pretty significant change in microgravity to back to Earth's gravity, and there's something called orthostatic intolerance. And if you think about it, like if you're tying your shoe and you stand up really quick or you move your body really quick and you kind of go, whoa, I'm a little lightheaded, that's an example of orthostatic intolerance. And how we counter that is through compression garments, so that we can at least try to control some of the fluid shifts and some of that impact for the crew when they come back on surface.
There are culturing living heart cells in microgravity and 3D printing cells. How is this going to keep astronauts safer?
I mean, it's kind of interesting when you say bioprinting heart cells in space. It almost sounds sci-fi, but that's where we are today. We actually work a lot with the ISS program, our partners over there from the science department, also the biological and physiological group over at the agency, and even the ISS National Lab on learning what are they understanding from these types of technologies? Because we think that if you can actually start to understand some of these complex 3D models, if they start to mimic kind of the in vivo or the body-like types of responses that we would see in our body, can we actually take a lot of that knowledge and say, maybe even think about precision health or personalized health for the crew as they start thinking about those long lunar missions, or as we go to Mars, how we can learn a lot about those responses, even just using some of those models.
Exactly. What is NASA doing to keep the astronauts' hearts safer during these long-term missions in space?
Yeah, and we actually, that's one of the things that we think a lot about. That's a big knowledge gap for us. Right now, on average, our crew are up in space for about 6 months, with a handful being about a year. In terms of even going beyond low Earth orbit, something that really has only really been done with the Apollo mission, with just a handful of crew exposed to this unique galactic cosmic radiation environment. That's a big knowledge gap for us. And so we need to think about duration. We need to think about these long-term health effects, especially exposed to galactic cosmic radiation for long-term health effects. So we're looking at CIPHER, which is this 14 studies that's integrated to see how that all impacts the human body in a period of time, over a period of time. And cardiovascular features or functions is an important part of that. So we got to think about radiation countermeasures. We got to keep our exercise and keep proper nutrition for these long duration missions.
Excellent. Dr. Fab, thank you very much.
Thank you. It's been a pleasure.
Over the years, we have expanded our research from answering the questions of if the heart could survive spaceflight to developing techniques for better cardiovascular health of astronauts on future space missions, and using that knowledge to contribute to better healthcare for all of us here on Earth. As always, we invite you to visit nasa.gov for more stories, blogs, updates, and media broadcasts. And that's Space to Ground this week. Thank you so much for watching.